Okay, this lesson is going to be 3.1, 3.2, and the beginning of 3.3. 3.1 is about scatterplots. You guys have all made scatterplots before. I trust you can make them, but there's a few new things we need to talk about. So in the past, you've called the x the independent variable and the y the dependent variable. In statistics, we are going to call them the explanatory variable, that's x, and the response variable is going to be y. Okay. X explains y. That's why they have those names. Oops. So explanatory and response variable, pretty straightforward, but you need to know those terms and you need to use those terms in stats. So, a couple of things here. Alcohol has many effects on the body. One effect is the drop in body temperature. To study this effect, researchers give several amounts of alcohol to mice and measure the change in each mouse's body temperature in the 15 minutes after taking the alcohol. The amount of alcohol is the explanatory variable. Change in temperature is the response variable. That's very clear explanatory and response variable. This one is not so clear. You could choose it either way. Jim wants to know the median SAT math and verbal scores in 51 states, including District of Columbia, are related. So he wants to know how math and verbal are related. He doesn't think either score explains the other. Jim has two related variables. Neither is an explanatory variable. Julie looks at some data and sees, can I predict the state's median SAT math score if I know the SAT verbal score? Julie is treating verbal as the explanatory variable and math as response. Both is perfectly fine. You might be right. Jim might be right that neither explains the other. You could choose either way and try to see the relationship. Okay. And we will make scatterplots. Okay. This is a scatterplot of the percent of graduates or seniors taking the SAT. Okay. Percent of graduates taking the SAT versus state average SAT math scores. Okay. Notice the ones with less taking the SAT have higher averages. So I'm going to explain a little bit about why. Why that is, these ones with 50, 60, 70, 80% are everybody taking the SAT. When this book was written, about the year 2000, I think it's 2002, so right after I graduated high school, this data is probably from when I was in high school. Midwestern states, everybody took the ACT. The schools in the Midwest only accepted the ACT, versus the schools on the coasts accepted the SAT only, not the ACT. So Midwestern kids, like Wisconsin, someone like me, I actually took the SAT because I was trying to get a scholarship. I don't know which one of these is Wisconsin, but it's going to be somewhere over here in this range, somewhere in this bubble. Only students trying to get either elite scholarships or good enough students that they were willing to spend the money to go to the East Coast or the West Coast to go to an elite college were taking the SAT. Thus, higher scores. Versus a state like Georgia, Georgia's somewhere, it's one of these down here. I don't remember which one. Had anybody that wanted to go to college took the SAT. So you ended up with a higher caliber. Those states with less had higher calibers of students taking the SAT versus pretty well almost everyone in the state. Idaho right now has, it's pretty much required for juniors in high school to take it. So it's going to be somewhere in the 90, 100%, whether or not you're going to college. And generally, those going to college score a little better as a general rule. So this data shows a trend that a larger percentage taking gets it's more accurate of the whole state, not just maybe the top end scores from the higher end students in your state. So there's your scatter plot. You've been making scatter plots for years. Examining a scatter plot, things we're looking for: overall pattern, any striking deviations from the overall pattern. You can describe the overall form of the scatter plot in form, direction, and strength of relationship, and any kind of deviation is an outlier or potentially what we will later call an influential observation. Scatter plots are positively associated. You've drawn regression lines through these things before. Positively associated when the regression has a positive slope. Negatively associated when the regression would have a negative slope, even if it's not linear. Well, you can think of positive as you get larger in the explanatory variable, you get larger in the response, versus negatively associated, as you get larger in the explanatory variable, you get smaller in the response variable. The next section, I'm going to get a little bit ahead, but we'll save a little time later. Correlation. The correlation coefficient is known as R. R is positive for positively associated and negative for negatively associated. We're going to talk about this example quickly because it's going to come up again later. The Sanchez household is about to install solar panels to reduce the cost of their heating in their house. In order to know how much the solar panels help, they record their gas consumption of natural gas before the panels are installed. Gas consumption is higher in colder weather, so the relationship between outside temperature and gas consumption is important. Table 3.1 gives data for 16 months. The response variable Y is the average amount of natural gas consumed each day during the month in hundreds of cubic feet. The explanatory variable X is the average number of heating degree days during the month. A heating degree day is usually a measure of demand for heating, and it's degrees below 65. So if it's 45, you get 20 degree days for that day. And this is for the month. This is obviously in a very kind of temperate climate. So this is their scatter plot. Shows a pretty linear relationship between average number of degree days per month, or basically how much do you need to run the heat, how cold is it, and the amount of gas used. Not all relationships are linear. Tips for drawing a scatter plot. Scale the horizontal and vertical axes. The intervals must be uniform. Okay. Do not give me 5, 15, 20, 40, 60. So notice they're counting each in a uniform interval. Really important. This should not be 5, this one 15, this one 20, 40, 60. They counted by 5s. That's important. Okay. Tip number 2. Label both axes. Do not just assume your teacher or anybody else knows what they are. Tip number 3, if you're given a grid, try to adopt a scale that makes use of your plot as a whole grid. There's one that really annoyed me from Carnegie Learning where they went 4 boxes and called it 5. So each box was 1 1/4. Really obnoxious. make it some logical amount. If you can go 2 is 5 and 2.5, that's kind of makes sense. But 1.25 is really weird. Don't go 3 for 5. Go 3 for 6. Or if that would be 2 each. Okay. Adding categorical variables. This is something I don't think you guys have ever done. So if you can't see this well, this is page 130 in the book. Notice that they labeled other states and southern states. So they just used a different mark to indicate 2 categories. They could have done this with like 4 marks or something. But what they wanted to see is it's generally thought of as the American South, which kind of means states that maybe would have qualified in the Confederacy back before the Civil War. South Carolina, Georgia, DC is considered in here. They've also labeled 4 of the kind of worst points. West Virginia, South Carolina, Georgia, and District of Columbia have some of the worst scores. They're kind of almost outliers low. Not completely, they're not far enough, but they are the edge of the low. So, Alabama is going to be somewhere in here, Mississippi, probably Louisiana. I don't know which ones did SAT back then versus ACT. But those are some of your southern states. And we can see that the southern states score on the low end, although they're not completely their own low. They're mixed in, but they're mixed in with the low for other states. Here's another example. Do the solar panels reduce gas usage? Well, here you've got the original graph of that speed without the solar panels. Now you've got the graph with the open circles being the solar panels. It's clear it does reduce gas usage, although not as much as I would have thought. Okay. You would have, I'm going to draw on a trend line. We will draw in least squares regression lines later, but this is just a trend line because I'm just kind of drawing it in. There's your initial trend line for the no solar panels. Here's your trend line for with solar panels. Kind of linear. It's hard to draw a line on this. It might be a little too high, but you can see the with solar panel definitely less gas consumption. Not sure if it's enough less to make it worth it, but there it is. So we definitely have evidence for less. We have evidence for worth putting in solar panels. That's a whole nother discussion. But a graph like this can help us look at the evidence and visualize it. Okay, you know how to make scatter plots on your calculator. I've taught all of you that in pre-calc and probably before that too. So I believe that is the end of 3.1. Now we're going to start correlation. Correlation says, how well does my data fit a line? It's not how well does it fit a curve, it's how well does it fit a line. Okay? Measures the direction and strength of the linear relationship. And here is your wonderful correlation formula. I'm going to make you use it once. Okay. Every other time you get to calculate correlation on your calculator, it shows up when you do the least squares regression line. If it doesn't show up, we will talk to me individually and we'll add it. I think I showed most of you how to get it added already. But this formula says 1 over the number of terms minus 1 times the sum of each x value minus the mean divided by the standard deviation and times each y value minus the mean times the standard deviation. So you'll take your x minus its mean times standard deviation, y minus the mean of y times standard deviation. And from there, you'll multiply those together. You'll do that for every point, add them up, multiply by 1 over n minus 1, and that gives you the correlation. Okay, we're going to do one by hand here in just a second. Okay, here's some scatter plots. The top one, okay, positive correlation. The bottom one, pretty good, but not amazing, positive correlation. Okay, so we're going to do this exercise 324 together. And we're going to calculate this by hand. I'm going to call the femur X, humerus Y. So there are 5 data points. 1 over n minus 1 is 1 over 4. Now, in order to get these data points, I need to know the mean and standard deviation. So you're going to enter them into your calculator, into list 1 and list 2, and calculate them. Okay. So I'm going to enter them into my calculator right here. We'll do the 84. I think I can do it a little quicker. That, edit. I'm going to clear out my first list because I don't think I need them. I'm going to clear up both lists right away. And I have a copy of the book, so I'm going to look at that instead of having them on the screen. Six, 64, 74. And these are dinosaur bones, the Archaeopteryx, based on fossils that have been discovered. So, no. Okay, stat calc, one variable stats. I have to do this for each list. And I will calculate. And I'm going to write this off to the side. X bar 58.2. SX 13.19. Now I have to do the same thing again, but with list 2. Still one variable stats. Now I need to do L2. And that's going to give me Y bar equal to 66, SY equal to 15.89. Okay, and now I'm going to go back to our book and that's the one I want. So X, I need to do all of these. 38 minus 58.7. It's not a very nice minus. Over 13.19 times 41. Now I'm doing the same thing for Y's. Plus, that's from my first point. Now I take my second Y. 70 minus 66. I'm moving over because I'm running out of space. So see how I'm taking each individual x minus the mean over the standard deviation. And then I'm taking each individual y minus the mean of y, which is 66 that I'm right now, over the standard deviation of y. And so this is how you do it by, oops, not 5.87, 58.7 over 13.19. And then you enter literally all of that into the calculator, add them up. Now, the easy way to do this on the calculator is not to enter that all one at a time. And I want you to see that's the formula. That's for 5 points. This would get to be a very big pain in the butt. I'm going to clear all of this away because I don't need it for the easy way to do the calculations. I can do stat calc, and if I do linear regression, I'm going to do a plus bx because that's what we do often in stats. Instead of mx plus b, there's a reason for a plus bx that shows up when we linearize nonlinear data. Store a regression equation, vars, scroll over to y vars function, y1, calculate correlation right here, R. There it is, 0.994. If I wrote out the numbers right, that calculation by hand would give you that. Okay? So there are some facts, though, that you need to know about correlation. Correlation is pretty easy to calculate with the calculator. That's what you're going to use. Okay? So, facts about correlation. Number one, correlation makes no distinction between explanatory and response. Basically, switching x and y in the equation doesn't matter because they're multiplied. You can multiply in either order. So for correlation, it doesn't matter. For regression that we're going to do tomorrow, it will actually at the end of today, it will matter. It's important for regression, but not for correlation. Okay. Correlation requires that both variables be quantitative. Okay, we had that scatter plot with the states, and we labeled categorical on the scatter plot, but it was still x and y, both explanatory and response, were quantitative, so you could do correlation on those. Number three, because R uses the standard values of the observations, that means mean and standard deviation, R does not change when we change the units of measurement of Y or X. So if you convert meters to centimeters or grams to kilograms or grams to pounds, the correlation won't change because it's using standardized values, which will adjust automatically. Okay? For positive R is associated with positive association, and negative R is associated with negative association. 5, correlation is always a number between -1 and 1, with numbers close to -1 or 1 being good. Strong correlation, the data fits a line well. Numbers close to 0 being doesn't fit a line at all, or you could say it fits a completely horizontal line through the middle of it. 0.5 isn't very good. It fits, there's a linear pattern to it, but doesn't fit very tightly. Okay. 6, correlation measures the strength of only a linear relationship between the two variables. Correlation does not describe curved relationships, no matter how strong they are. And 7, like the mean and standard deviation, correlation is not resistant. Thus, it is strongly affected by outliers and what's called influential observations, which we'll talk about tomorrow. Okay. The scatter plot in figure 3.9 shows a bunch of things. So here we've got some correlation. Correlation 0, no discernible pattern. Once in a while, you will get some correlation matching. Match it. Correlation negative 0.3 appears to be going downward, but it does not fit very well. Correlation 0.5 fits a little bit better than that 0.3 and is going upward. Correlation negative 0.7 definitely going down, fits all right. Correlation 0.9, definitely positive, fits reasonably decently. Correlation 0.99 fits this line that I can't make straight really well, and is in the negative direction. Okay. That is correlation. Okay, we are going to start least squares regression today and finish it tomorrow. So correlation measures the strength of the linear relationship. I have to flip over to 3.3 scan. Okay. The least squares regression is finding the line. A regression line is a straight line that describes how a response variable y changes as the explanatory variable x changes. We often use a regression line to predict the value of y given a value of x. Regression, unlike correlation, requires a explanatory and response variable. Okay, we will be talking about the least squares regression line. It's the one that's used by far the most in anything. It is known as a mathematical model. Least squares regression line will often be abbreviated LSRL. This book. Okay. So, again, you know how to calculate it on your calculator. That's what we're mostly going to be doing. Okay. Except on occasion when we are going to give you some other data about it. Okay. So here's the scatter plot of the Sanchez house again and their gas usage. There's a nice least squares regression line plotted through it. We could predict how much they're going to have to pay if they need 20 heating degree days in a month. Okay. I actually think this is graphing the average per day. But the idea being that if I need 20, I can easily make this prediction from the equation generated. It looks like it's just short of 5 from the graph, but I can get an exact from the equation generated by the least squares regression line. Okay. Okay, there is a distance from the actual predicted to the observed. The idea with the least squares regression line is we are going to take this distance here, known as the residual. That one above the line is positive. This one is a negative residual. It's another negative residual. So observed minus predicted is called the error. The least squares regression line is about minimizing that error squared. So the value of the error squared minimal. If you just do the value of the error, it should come out to be 0 because you got some positive, some negative, and they should add up to 0. So that's why they do squared. Squared makes them all positive. We minimize the squared errors. Okay. A couple of things to note. The equation for the least squares regression line. This little thing here, we have y hat. Y hat means predicted y value. You have a table full of y values that you actually got. Y hat means the predicted y value for a given x. In this case, A is my y-intercept and B is my slope. Okay? Yes, it's written backwards. Get used to it. That's how we do it in stats. And it has to do with how we deal with nonlinear regression. It's much easier in this order for nonlinear. To calculate my y-intercept and my slope, because usually I have y equals mx plus b. I know m and b and y and x stay the same. Well, now we'll have y hat equals a plus bx, and I'll know a and b. And x will be a independent variable. Okay. So the formula for the slope, b, my slope, is equal to r, the correlation coefficient, times standard deviation of y over standard deviation of x. There it is, correlation coefficient. And this is important. This is a nice formula. If you have all the data, you're just going to let the calculator do it for you. But sometimes they will give you statistics like, here's the correlation. Here is the standard deviation of y. Here's the standard deviation of x. The y-intercept is y bar, or mean of y, minus this slope that we just calculated times x bar. An interesting property of the least squares regression line is it always goes through x bar, y bar. So it always goes to the point of the average x and the average y. It will 100% of the time go through that coordinate. Okay. It's a little bit strange. Let's go through one example of this, and then we will be done with the lesson for today. So we're going to use those things. So suppose we have this. Notice it gave me all my data. I've got x bar, I've got y bar, I've got sx, I've got sy, and I've got r. So if I want the equation for the least squares regression, B is R.997 over sy, it's y over x, just like slope, because this is slope. Standard deviation of y over standard deviation of x. And they calculated that for me below in the example. To get A, I do y bar. So here this is r sy over sx. And here we have y bar minus b x bar. B, I just calculated 1.695 X bar is 17.222. And that is equal to 131.920. The equation y hat equals a plus bx. So my actual equation is y hat equals 131.920 plus b 1.695x. That is the equation for my least squares regression line. I just had to use the formulas and plug in the variables. If they give you what's called stats or statistics on your data, they give you your actual data. Again, you're going to do it with your graphing calculator. Okay, that is scatterplots, correlation, and the beginning of least squares regression. We'll go more into least squares regression tomorrow.